Okay, please mute yourself, guys. Okay. Good evening, guys. Let's continue our discussion. Before we start today's class, let us see what we discussed yesterday in the last class. We discussed about various design methods. Namely, we talked about working stress method, ultimate load method, and limit state method. We talk about drawbacks on each and every method, and we said that final method that we are using currently is limit state method. Then we talked about stress strain behavior of concrete and steel, how is the stress strain relation, then how we use the partial safety factors, we discussed them. We talked about characteristic strength. We said that characteristic strength is nothing but a strength whose value is always in the 95% of the times, the value is more or equal to the given value. That's what is called characteristic strength of concrete. Then partial safety factors we discussed. We said that partial safety factor is something that usually apply to both loads and materials. We said that because material properties are not same all the time, so a lot of quality issues involved. That's why we divide the strength of the material by partial safety factor. Otherwise, on the load side, we know that expected load, but then to get more factor of safety, we multiply the load with partial safety factor. That's what we do. Guys, there's some noise, guys. Please mute yourself, guys. Some of you are making some noise. Please mute yourself. Okay. Let me continue. Okay. Yeah. Then we talked about different types of sections. One is we talked about balance section. Again, before we talked about various sections, we talked about stress block parameters. Stress block parameters wherein we found what is the compression force acting, what is the total tensile force acting, then the total force, and then we found the distance where that is acting. Those are nothing but stress block parameters. After that, based on the depth of neutral axis, we divide the section into balance section, under reinforced section, and over reinforced section. And I said that balance section is a section where strain in the cement and concrete will reach at the same time. Whereas an under reinforced section, compared to neutral axis of a balance section, the depth of neutral axis will be less for under reinforced section. And here the steel will strain more as compared to concrete. And on contrary to that, in the over reinforced section, the depth of neutral axis of over reinforced section is more than that of a balance section. And the strain in this case is the concrete level. On concrete, the strain level is, concrete reaches the highest strain level as compared to the steel in case of over reinforced section. That's why the discussion we made in the last class. Okay. Now in this class, what we do is here is today's class, guys, or today's learning outcomes. So by end of the class, you will be in a position to analyze the single reinforced sections. When I say analyze, because we will be given dimensions and reinforcement, you will be in a position to compute what is the moment of resistance of the given section. Similarly, we'll understand what is the doubly reinforced section, and we'll try to analyze some doubly reinforced sections, in the sense how to find out area of reinforcement and how to find out moment of resistance of a given doubly reinforced sections. Then we'll also design for shear today. We'll see how to design for shear, what are the steps involved, and we'll solve a numerical problem on that. And finally, we'll discuss today about development length or anchorage length, why that is required and how to compute that. So these are the topics for today. Well, let's continue, guys. So before we start the discussion, let's quickly recap the notations we use in the reinforced concrete design. So one is XU. XU is nothing but depth of neutral axis. Depth of neutral axis of a given section. That's what we denote them with X of XU. Okay. Then XU max or XU limit. That means it's this depth of neutral axis of a balanced section. Okay. B is nothing but width of the section. So when you're talking about rectangular beams, I'm talking about the B is nothing but width of the rectangular section. Then D, small d. Small d is the effective depth of the given section. That means from the topmost fiber to center of the tensile reinforcement. That's what is the small d value. Capital D is the overall depth of the section. That means from topmost fiber to bottommost fiber, including the cover. That is whatever D value. Then MUD value. MUD is nothing but the U, nothing but ultimate. D stands for design. That's ultimate design moment. So this is a moment, design moment. Then here MU limit. Here U means ultimate. Limit means we use for the balance section. So this MU limit stands for this is a moment of resistance of a balanced section. Okay. Then FCK is a characteristic strength of concrete. FI is characteristic strength of steel. Okay. So if you're using a Fe 415 steel, HYSD bars, then Fi is taken as 415. If you're using mild steel, then Fi is taken as 250. Similarly, FCK, if you're using M20 grade concrete, we take characteristic strength as 20 Newton per mm square. As if you're using M30 grade concrete, we take FCK as 30 Newton per mm square. That's how it is. These are the standard notations we use in the design of reinforced concrete. Okay. So now let us see, guys, what's a singly reinforced beam means. Because beams, right, we classify them into two categories. One is based on the position of neutral axis. That's what we discussed in the last class. So based on that, we can design them as either a balance section, under reinforced or over reinforced. Now, again, you can classify the beams into two types. One is singly reinforced beams, other one is doubly reinforced beam. Singly reinforced beam means, so as you can see in the picture, guys, the reinforcement is provided only in the tension zone. So this line, this is the neutral axis. So below this is a tension zone, above that is a compression zone, assuming that beam is bending in like this, like in the shape, positive bending moment shape, basically the sagging moment. If I have sagging moment, assuming that beam is bending in this shape, and the bottom is subjected to tensile stresses and the top is subject to compressive stresses. And in the singly reinforced beams, we provide the reinforcement only in the tension zone. Okay, so this what is called singly reinforced beam. Okay, but then mathematical how to classify the beam as singly reinforced beam. So here is the equation, guys. So we go for singly reinforced beam when design moment, ultimate design moment is less than the moment of resistance of a balance section. So we'll compute what is the design moment based on our loading and support conditions, the maximum moment. And then we'll compute what is the moment of resistance of a balance section. Okay, we'll compute this also. Then we'll compare both of them. If your design moment is less than that of a balance section, then we'll go for singly reinforced beams. This was the concept. Okay, so AST, right, area of reinforcement, area of steel reinforcement, or area of reinforcement. So ST stands for area of steel reinforcement in tension zone. T stands for tension. That means AST stands for area of steel in tension zone. Okay, because we are providing reinforcement only in the tension zone in case of singly reinforced beams. So AST is computed using the equation as we saw yesterday, right? Equations are 96, page number 96. We have G 1.1. We use those equations to find out AST value. Okay. Now let's talk a little deeper, a little in depth about singly reinforced beams. In the course point of view, you can expect two questions, guys. One is certainly analysis type is computing moment of resistance of a singly reinforced beam. That means dimensions and AST will be given to you. So you will be asked to find out what is the moment of resistance of the section. Or else in the section B part of your question paper, they may give you a load and you need to find out moment of resistance and just find out AST. That's it. That's simple problem, not complete design. If that is the case, if first case you want to find out analysis problem, you want to do analysis problem where you are asked to find out only moment of resistance of the given rectangular beam, then here are the steps, guys. The first what we do is we'll find out what is the depth of neutral axis. We'll take a given section, we'll find out what is the depth of neutral axis, XC value. Then we compare that with depth of neutral axis of a balance section. Okay. Then we classify whether, okay, based on these two, we classify that what kind of section is that. Then we go to page number 96 of IS 456-2000 and use appropriate equation to find out moment of resistance. The simple steps to find out moment of resistance of singly reinforced beams. Other hand,
sir, you're not audible, sir.
It's not audible. Okay. Now it's clear, guys. Or is it audible now? Your voice is breaking though. Okay, let me see. Let me continue for 2 minutes. Let us see. Okay, here is the computing area of reinforcement. Okay, just a moment, yes. If you want to find out the area of reinforcement, so what we do is first is you find out the design moment. What is the design moment? Okay, once you know the moment, you compare moment with that of a balance section. Then we use appropriate equation again based on whether MUD value is less or more. Then based on that, again we'll find out what is the area of reinforcement, whether it is equal to mu limit value, or it's becoming under reinforced section or over reinforced section. We classify them again, then we use appropriate equation to find out area of reinforcement. Is this clear, guys? Is it audible now?
No,
No, it's not
no,
audible.
sir.
Hello.
Voice is breaking, sir.
Check your connectivity, guys. Actually, here I have full network. Network is fine. Let me. So I'm holding my mic also near to this. Let me see. This okay, guys? Now. Nikhil, is it audible now? It's dropped. Others guys are able to hear my voice?
Yes, sir.
Okay, ma. Okay. Okay, let's find out. Next thing is computing the area of reinforcement. So to finding out computing area of reinforcement, we'll find out what is the design moment. Again, we need to classify here, assuming that's a singly reinforced section. Then we'll find out what is the moment of resistance of a balanced section. So based on that, we'll find out AST value. Okay. So let's see, work out a numerical problem. Okay. Yes, okay. So here's the one, guys. Let me read it out for you. I'll share the slides for the class. So find the moment of resistance of a singly reinforced concrete beam. Beam is missing. Concrete beam of 200 mm width and 400 mm effective depth. Reinforced with 3 of 16 diameter bars of Fe415 steel. Take M20 grade concrete. So what is the question? So what I'm doing is, because here the dimensions are given, saying width is 200 mm, overall effective depth is 400 mm. Effective itself is given 400 mm. So it's asking us to use M20 grade concrete and Fe415 steel. So I have to find what is the moment of resistance. So because from this look, we don't know, because he said that area of reinforcement is only in one portion. That means he's talking about only reinforcement in tensile region, tension region. That means it's a singly reinforced beam. Okay. Now, first thing what we need to do is we need to classify the section. So I have given data I have written here. AST, he has given 3 bars of 16 mm diameter. Find what is AST. Okay, and this is not required. Okay, then I find out what is FUXU by D value. XU by D value is basically from this equation. We have page number 96, right? XU by D is 0.36 FCK BD. So we use that equation to find out XU by D value. Once you get XU by D value, then I'll find out from page number 70. I have given code reference here, guys. From page number 70 of IS code, we use this XU max by D value. Then we get for Fe415 0.479. For given section, we got XU by D as 0.378. Compare. When you compare, XU by D value is becoming less than XU max by D. That means it's basically under reinforced section. So that's how we classify it. We'll find out what is XU by D value, then find out what is XU max by D value. Compare both of them. Now, because XU by D is less than XU max by D, we categorize this as under reinforced section. Okay. Now, when under reinforced section, then I'll use appropriate equation to find out moment of resistance. So from page number 96 of IS code, we get this equation. Moment of resistance of a under reinforced section is given by this equation: 0.87 Fi AST D into 1 minus AST Fi by BDFCK. Substitute all the values. Fi is characteristic strength of steel, which is given as 415. AST 3 bars of 16. So effective depth is given as 400. That's what I have written, 400 into 1 minus AST Fi divided by width is 200, effective depth is 400, and M20 grade concrete. We substitute all the parameters and compute moment of resistance. That's simple. Okay. This is how we find out moment of resistance of the given section. Okay. Okay. Next, let's get in. Once this is done, okay, so if you have any questions, please feel free to ask during the class itself. No problem. We'll have discussion also. Okay. So this about singly reinforced beams. Okay, I'm doing only very small problems, but next class we'll do the complete design, A to Z. Like in the sense, for you take a beam, we'll do everything, including shear design, development, and everything. But here I'm talking about part B questions. Like if you were asked to find out moment of resistance of singly reinforced beam, or simply some reinforcement of a doubly reinforced beam, or concepts we're discussing here. Okay, so this is how we find out moment of resistance of a singly reinforced beams. Okay. Now let's move on to doubly reinforced beams. So in contrast to singly reinforced beams, in the doubly reinforced beams, you provide the main reinforcement both in tension zone and in the compression zone. Assuming beam is bending in sagging condition, it's having a positive bending moment, it's having a, let's say, sagging bending moment. So when you have a sagging bending moment, then bottom is subjected to tensile stresses, top is subjected to compression stresses. In case of doubly reinforced beams, we provide the main reinforcement in both the phases, both in tension zone and compression zone. So we call this AST, area of steel in the tension zone. We denote this with ASC, area of steel in compression zone. So we'll design both of them in case of doubly reinforced beams. Now let's say what are the conditions when we go for doubly reinforced beams. So mathematically, we'll find out what is the ultimate design moment for a given load and support condition. Then we'll find out what is the moment of resistance of a balance section. Compare both of them. So if for a design moment for which you're supposed to design value is more than bending moment of your moment of resistance of a balance section, then we have to go for doubly reinforced beam. If your design moment is less than that of a balance section, we go for singly reinforced beams. But if design moment is more than that of a balance section, then we go for doubly reinforced beams. That's how it is. That means here the beam cannot take moment more than that of a balance section. No beam can take. That's why we have to go for design of doubly reinforced beams. Okay. Because singly reinforced beam cannot take moment more than that of a balance section. So the moment your moment is little more than moment of your resistance of a balance section, then we go for doubly reinforced beams. This is what is the simple concept. Now let us see what are the steps. Like one is that why we go for doubly reinforced beams. What are the conditions? What are the circumstances when we go for doubly reinforced beams? So it is the one when the dimensions are restricted because we want to have a clear floor height, or you have some other site restrictions where we cannot increase the depth of the beam. Then in that case, or width of the beam, in that case we go for doubly reinforced sections. Or moment of resistance of singly reinforced section is less than that of a external moments. If this is the case, or when loads are alternatively reversing. So sometimes because of the load condition, we get sometimes beam is subjected to sagging moment, sometimes it is subjected to hogging moment. So if moments are itself are changing because of the load position, then that time we go for doubly reinforced beams. Or else when the loads are eccentric, so loads are not exactly acting at the center, but is having some eccentricity, then we go for doubly
Sir,
reinforced beams. Yeah.
sir, once explain first point, sir.
Yeah, when the dimensions are restricted. So example, say in the site when you construct the beams, okay, so you will not have enough space to increase the width or increase the depth because of site conditions. Maybe you want to have a clear height somewhere, or you have adjacent property, some other property is there, your boundary is there for your land, so you can't increase further dimensions of your beam on the top. Or you have some issues in the construction where you cannot increase the dimensions, you can't have infinite width or infinite depth. So in that case, what we do is we restrict the dimensions, but you go for doubly reinforced beams. Example, say you are getting depth as about say 800 mm and 900 mm as the depth for ground floor. So it doesn't look good when you provide so much of deep beams. So you want to reduce the depth, because when you provide more depth, what happens is the distance between the floor and the roof, effective distance, clear space will be reduced. So you don't want to have so much of depth. So then what we do is we go for doubly reinforced beams. Or and moment of resistance of singly reinforced section is less than that of a external moment. That means that's what is the same point. Your moment of resistance is less than the singly reinforced moment. Reinforced section cannot take the moments. That means maximum it can take is only mu limit value. That means if your design moments are more than mu limit value, that is what is the second part of this sentence. Moment of resistance of the singly reinforced section. That means singly reinforced section can take moment maximum up to mu limit value. But if your external moment, that means the design moment is more than that of mu limit value. Other way around is the same as this. Your MUD value is greater than mu limit value. Then we go for doubly reinforced beams. Is that clear, guys?
Yes, sir. Yes, sir.
Okay, ma. Okay. Then when the loads are eccentric, so when you have eccentricity on the loads, or the beam is subjected to accidental or sudden lateral loads. Like if we are expecting some vehicle may come and hit your structure in the beams, or accidentally something may happen. So if you're expecting those cases, then also we go for doubly reinforced beams. Okay. Then in case of continuous beams or the slabs, also the sections that supports are generally designed as doubly reinforced beams. Because in case of continuous beams or slabs, the supports, right, the supports negative bending moment happens sometimes. So when you have negative bending moment, then your tensile zone and compression zone will be alternative. Okay, when you have negative bending moment or positive bending moment. So because bending moment sign changes, so in that case also we go for doubly reinforced beams. So these are some of the areas, some of the conditions under which we usually prefer doubly reinforced beams. Okay. Okay, now let us look at the section, guys. Doubly reinforced beam. Like how do we do the design? So this what is the doubly reinforced beam? Okay, just a moment, guys. Okay. Spotlight. Okay, just a minute. Okay. Look at this, guys. So this what is your doubly reinforced beam. Okay. Yeah, I want to use just a moment, guys. Okay. This is your doubly reinforced beam as you're seeing here. Okay. So this is a doubly reinforced beam. So we have the reinforcement both in the tension zone and compression zone. This what is so this is designed in two parts. One is we'll design separately what is known as AST value. Our AST again we divide into two parts, AST1, and then we design what is known as AST2. Then we add both of them, we get AST, total area of steel in tension zone. Then we separately design area of steel in compression zone. So AST1 is nothing but area of steel required for a balanced section. So we'll take all the moment, or we'll do all the design moment calculations. Then we'll find out what is AST1. AST1 is nothing but area of steel for a balanced section. We'll see how to do that. Then we'll find out for the rest of the moments, we'll find out what is AST2. We add both of them together, we get what is total area of steel in the tension zone. Then we'll separately find out what is ASC value, area of steel in the compression zone. Okay. If you go to page number 96 and clause G1.2, then we see the relevant clauses for doubly reinforced section. Let me show you guys. Let me show you the clause for doubly reinforced section. Here. Let me put new shear. Do we have that? Okay. So can you open this? Just a moment, guys. Let me open the page. New share. Okay. Share. Okay. Can you see IS code, guys, now?
Sir.
Yes, sir.
Yeah. Okay. Okay. Let me continue here. So if you go to page number 96 here, so G1.2. G1.2 talks about section with compression reinforcement. That means we're talking about doubly reinforced sections here. So where the ultimate moment of resistance of section, let's see, of a section exceeds limiting value. That means if MUD value is more than MU limit value, compression reinforcement may be obtained from the following equation. So we use this equation to find out ASC value. That means we know what is design moment, we know what is MU limit value. I'll tell you what is FSC. FSC is nothing but stresses in the steel. Then we know what is D value, effective depth. D dash is the cover that you provided on the compression reinforcement, the total cover. Okay. effective cover that you provide here. So once you know all the parameters, you can find out ASC from this equation. Okay. So what do we do, right? To get FSC value, FSC is nothing but the stresses in the steel at a strain of this value. That means we'll find out what is the strain using this equation. So this equation will give you the strain 0.0035 into Xc max minus D dash by Xc max. This will give you the strain. Then we go back to the graph what you saw yesterday, the stress strain curves for the steel. Okay, from those graphs we'll find out what is the stress, corresponding stress for this strain. The stress value we'll take it as FSC value. Then we substitute FSC here, we'll get ASC value. This is how we find out ASC. But if you want to find out AST value, see again he said that AST is nothing but AST1 plus AST2. AST1 is nothing but area of tensile reinforcement for a singly reinforced section for MU limit value. That means you design area of steel for a balanced section. So we find out AST1 using this equation. You see here, the left side XU by D. Here, this is what is the, in this formula, we use A instead of AST, put AST1, the instead of XU, you use XC limit value. So when you know XC limit by D, from page number 70, we'll get what is XC limit by D value. Then we know what kind of grade of steel we are using. Then the FI is known. Then based on grade of concrete we are using, we know what is FCK. You know what is width of the section, depth of the section. They can find out AST1. That will give you the AST1. That means that is the area of reinforcement for a balanced section. That you get it AST1 from this equation. Okay. Then AST2 we get from this equation. ASC divided into FSC by 0.875. We use this equation. Again, ASC is nothing but, again, code is given here. So ASC, instead of ASC, you can use this formula. MU minus MU limit divided by FSC into D minus D dash. You take these two parameters other side, you'll get ASC value. So that ASC we'll use here, we'll find out what is AST2. Okay. But for now, we remember that all the equations are available. Some of the equations are available on page number 96. This is how it is. Okay. Let's go back. We'll see an example how to compute this. Okay. Now let us see. Here are the steps for finding out. Okay. Let me see, guys. Okay. So we have seen the provisions. Now let us see what are the steps how to find out the moment of resistance. Let's talk about analysis problem. Yeah, tell me, guys. Someone has raised hand.
Sir, with experiment Telugu, sir, we will understand a little more.
Sorry, which one?
Sir, please explain in Telugu, sir, we will understand a little more.
No, we'll talk numerical problems again. So I'm just explaining the procedure. Again, we have numerical problems to work on.
No, I'm not. No, sir. I'm saying that can you explain in Telugu, sir? I mean, it's a little comfortable to understand.
Okay, but actually, okay, I'll try to put some words in Telugu also. Because I'm not very comfortable in complete Telugu, but I'll put the words. Okay, good. I'll include that. Okay. Okay.
Sir,
Ma. Cheppandi.
sir, one doubt, sir.
Cheppma.
Sir, why will take AST, AST1 and AST2, sir, when we can provide only one AST, na, sir?
No, we provide only one AST, but the way how we compute is we'll divide them into two parts. Because we want to find out total.
Why dividing, sir?
That's how the analysis is done. Because we'll find, because moment of resistance, right? Design moment is more than that of a balance section, right? So we'll find
Yes,
out
sir.
the area of reinforcement required for a balance section in one part. Then we'll find out for the difference moment in the sense design moment minus MU limit value. That is the differential moment value. For that moment, we'll provide reinforcement separately. Like for that moment, how much reinforcement is required in tension zone, how much reinforcement is required in compression zone, we'll find out separately. Because that's what is called analysis.
Sir, why can't we take more a complete ultimate tension, sir?
Which ultimate tension?
Sir, we are providing AST1 and AST2, na, sir. We'll provide only one. We'll provide AST for tension and compression different, na, sir.
Yeah, ASC is where this one. In tension zone, what we provide is AST. But in the compression zone, we provide what is ASC.
Sir, that's what, sir, I'm saying. We can provide ultimate moment and we can calculate AST1, ultimate, no, sir. Why one and two?
That's what I'm saying here. See, AST1 way we're providing is because we are doing the part into two parts. Because your design moment is more than that of a balance section, right? If it is a balance section, Then we have the direct analysis. You have direct equations to find out AST value. Because here the moment is more than AST value, more than MU limit value. Moment, actual design moment is more than that, right? So that means your reinforcement is
Yes, sir.
supposed to be more than that of a balance section. Okay.
Yeah,
So
okay,
that
sir.
means we'll find out how much is required for a balance section. Plus we'll find out how much more is to be added. So we're doing with two parts. Because that we are doing two parts because if design moment is more than that of a balance section. That is the reason why we are doing it in two parts.
Okay, sir.
Okay. Okay, good.
Yes, sir.
Okay, ma. Let us see, guys. ఇప్పుడు స్టెప్స్ చూసారు అనుకోండి, స్టెప్స్ ఫర్ ఫైండింగ్ అవుట్ మొమెంట్ ఆఫ్ రెసిస్టెన్స్. సో మీరు మొమెంట్ ఆఫ్ రెసిస్టెన్స్ ఫైండ్ అవుట్ చేయాలి. సో యూ వాంట్ టు ఫైండ్ అవుట్ హౌ టు ఫైండ్ మొమెంట్ ఆఫ్ రెసిస్టెన్స్. Steps, here are the steps, guys. First, what we do is you find out what is the depth of neutral axis. మీ ఇచ్చిన beam కి you find out depth of neutral axis using this equation. This equation is not available on IS code directly, guys. So you got to remember for W reinforced beams, this equation you got to remember, guys. Just to గుర్తుపెట్టుకోండి. Only thing is this equation is available. 0.87 Fi AST by 0.36 FCK BD is available. But then for W reinforced beams, we deduct FSC ASC value. So much of stress are deducted in the numerator to find out depth of neutral axis. Okay, once you know depth of neutral axis, then you find out stresses in the strain in the steel. Once you know strain in the steel, you find out what is the stresses in the steel. So మనకు strain తెలిసింది అనుకోండి, the stress calculate చేయండి using these equations. Again, stresses are found out using whether it is HYST bar or mild steel bar. HYST bar అనుకోండి, you use this equation, directly graphs తీసుకుంటాం. If it is a mild steel, then use this equation. So these are the steps, guys, how to find out moment of resistance of W reinforced sections. So W reinforced section is little different approach. Okay. So first is XU by D. Then I want to find out what is the stresses. To find the stress, you find out what is strain first. Strain calculate chestam. Once you know the strain, then based on whether you're using HYSD bar or mild steel bar. If you're using mild steel bar, then we use this equation to find out the stresses in steel. And if you're using HYSD bar, then use this equation to find out the stress directly. I mean, use the graphs on page number 70 to find out the stresses in the steel. Okay. Once you know stress levels in the steel, then we use this equation. Then we compare XU max value. XU max value again as it is. XU max by D value we have, right? Based on grade of steel. At page number 70 lo undadi. So దాని నుంచి you find out what is XU max by D value. Then you will find out XU max. So first step, you know what is XU value. Then here you find out what is XU max by value, XU max value. Once you know, you compare both of them. If XU value is less than XU max value, then that is under reinforced section. If it is under reinforced section, then moment of resistance is calculated using this equation. 0.36 FCK BD square. So this is again for your MU limit value, similar to equation as MU limit value, but there is no limit here. We use XU value. Plus, because you are providing again compression reinforcement, so that is FSC minus FCC into AS into D minus D dash. This is one more equation. This is what we use to find out the moment of resistance of a under reinforced section, under reinforced W reinforced section. Okay, so basically when you add everything, this is what you get: 2.6 FCK BD square plus FSC into AS into D minus D dash. So you don't take this is a different factor. You directly find out FSC value. This is what we get from the graph or from the formula. So we use this equation. This is only derivation, don't worry. Whatever there in the box, we use this formula to find out moment of resistance. If at all, if XU is less than XU max value for W reinforced section. Otherwise, if you get XU value is greater than XU limit value, XU max value for W reinforced section, then we use this formula. So instead of XU, same as the previous formula here, instead of XU by D, I use XU limit by D. That's the only difference. Use this equation to find out the moment of resistance of W reinforced section. But only difference is the issue is with finding out the stresses in the steel, FSC value. To get FSC value, you have to find out the strain, epsilon SC value. You find out epsilon SC value, then you find out FSC value, then we use the value here. So these are two different approaches. Though again, repeating the steps, guys. So first is you find out XU by D. తర్వాత strain calculate చేయండి, strain in steel. Strain తెలిసింది అనుకోండి, then you find out stresses in steel. Again, based on whether you are using a mild steel or we are using HYSD steel. Okay. ఒకసారి FSC తెలిసింది అనుకోండి, then you find out what is XU max by D. Then you compare XU and XU max. రెండు compare చేసుకోండి. If XU is less than XU max, use this equation to find out moment of resistance. లేదు మీకు XU కనుక more than XU max అనుకోండి, it's more than XU max, then use this equation to find out moment of resistance. So you have to by heart these steps, guys, for doubly reinforced sections, how to find out moment of resistance. Okay, let me work out a numerical problem చూపెడతాను. Okay, so let me read it here. Find the factored moment of resistance of an RCC beam size 300 by 300 mm by 450 mm effective. The bracket, that means 450 mm is given as effective depth. The beam is reinforced with 4 of 25 mm dia bars in the tension zone and 2 of 20 mm dia bars placed at the distance of 50 mm from the top of the compression zone. That means D dash is given as 50 mm. Use M20 grade concrete and Fe415 steel. This what is that. Now problem చూసారనుకోండి, problem already two reinforcements ఉన్నాయి. ఒకటి, one thing he is talking about tensile reinforcement, ఇంకోటి compression reinforcement. So రెండు ఇచ్చారు కాబట్టి it is a doubly reinforced section. That's the first question. Okay, it is a doubly reinforced section. Then you write down the given data. So he said that what is the size of the beam, 300, width is 300, effective depth is 450. Then AST value, total reinforcement in the tensile zone is 4 of 25. Then ASC value is 2 of 20 bars. That means area is 2 into pi by 4 and 20 square. The small D dash value. D dash is nothing but the effective cover provided to the compression zone, the compression reinforcement. That's 15 mm undi. So M20 grade concrete Fe415 ichadu. So again, based on the steps, I'll find out what is the XC max first. Okay, the last step, but I found XC max based on page number 70. For page number 70 lo chusaru anukunna IS code lo Fe415 steel ki XC max is 0.48. So I'll find out D value has given 450. So 450 into 0.48, I get 216. Now I'll find out AST, 4 bars of 25 mm diameter. ASC, 2 bars of 20 mm. So I just found the reinforcement, area of reinforcement. ఇప్పుడు XU క్యాలిక్యులేట్ చేశాను. XU by D is given by this equation, 0.87 Fy AST minus FSC ASC by 0.36 FCK BD. దీంట్లో అన్ని తెలుసు ఎక్సెప్ట్ FSC వాల్యూ. FSC కావాలంటే స్ట్రెసెస్ ఇన్ స్టీల్, ఇది కావాలంటే వీ షుడ్ నో వాట్ ఇస్ స్ట్రెయిన్ ఇన్ స్టీల్. సో స్ట్రెయిన్ క్యాలిక్యులేట్ చేయడానికి ఈక్వేషన్ ఇది 0.0035 XU max minus D dash by XU max. So we know everything. I substituted everything. XU max ఇక్కడ నుంచి వచ్చింది XU max value 216 minus D dash. D dash is cover to compression reinforcement. అది 50 mm ఇచ్చారు. సో XU max by D is 216. సో టోటల్ స్ట్రెయిన్ వచ్చి 0.0026 వచ్చింది. ఓకే, నెక్స్ట్ మీరు గ్రాఫ్ చూసారనుకోండి, ఫ్రమ్ పేజ్ నెంబర్ 70లో గ్రాఫ్ చూసారనుకోండి, ఐ షో యూ ద గ్రాఫ్ ఆల్సో. How much? 0.0026. You go to page number 70. Let me open the IS code for you guys. So IS code, page number 70. Let me go to page number 70 of IS code. Where are we? This is page number 38. Okay. Page number 70 of IS code, 58. Page number 70. 72. Okay. This is page number 70. Okay. The page number 70. Guys, if you get disconnected, join again. Okay. It's going to be over. I'm just explaining. So 0.0036. How much did you get? 0.00. Let me see. The value is 0.0026. Okay. 0.0026 means, open this case. Can you see this IS code, guys?
Sir.
Okay. See, 0.0026 is the strain. So if it is 0.002, then in this design curve, the value is somewhere 0.85.